In this, we are going to learn how to solve a differential equation using what we call the Heaviside function. So when the input function is a piecewise function, we're going to use this technique. So, so we can say use when the input function is piecewise. So for example, so we can look at a differential equation like this. So let's say we have x double prime plus 2x prime minus 3x equal the input function ft, where t is the independent variable, like that, where the ft is a piecewise function, function such that, let's say for example, we have ft which is t if um, t is less than pi over 2, and then maybe sine t if t is greater than or equal to pi over 2. So like a situation like that. So what is the shape of the graph? So let's see the graph here. So you can see that uh, until pi over 2, you can see that until pi over 2, it is like a y equal x type of graph. So this is until pi over 2. So this is open because that point is not there. So this is pi over 2. And then what happened right after pi over 2, it's going to jump to, so this is like pi over 2, okay? Pi over 2. And then right after pi over 2, it's going to jump to the sine function. But we know that at pi over 2, sine is 1. So this jump to 1 and then start following the sine graph. So that means it's going to go like that, go like that. So that's the situation. So that's what the shape of the graph in this situation. So this is exactly 1. So yeah, so the question is, what are you gonna do? So that's the input function. That means you're gonna send this signal, let's say signal, to a differential system, and then we are expecting the output. So we are looking for what the output is. So that's the kind of situation we do. So we have this kind of input function to a system, and then we are looking for what is the output. So the question is how to solve such a differential equation using the Laplace transform method. So let's see. I mean, it's not that difficult actually. We're gonna use the Heaviside function for that, the step function. So let's talk about the theory behind that. So the question is, we need to represent a signal, like piecewise signal, as a single function before we do that, and then we can use the transforms to do it. So, so the major question is how to represent um, how to represent such a function. So that's the major question. So let's answer that first. So we already know this function. We talk about what the Heaviside function. We normally write ut. That's the basic one. So what is that? It is 1 if t greater than or equal 0, and 0 if, or the otherwise 0 if t less than 0. So that means if you look at the graph, so the graph of this function is, so it's going to be 0 until, so it's 0 until 0 is 0, and right after 0 it's going to jump to 1, and then it stays at 1. So these are like what we normally call the switching function, because it looks like a switch. It's going to switch right after 0 is jump to value 1. And then we also look at the general case of this one, what we normally call the shifted version of this one. Um, so what's the shifted version, which is u, we normally call t minus a, so shifted by a. So what's going to happen? It is 1 if t greater than or equal a. It is 0 otherwise. 0 otherwise. So this is like a general Heaviside function. There's another notation. So this also we write as h for the Heaviside function, a for the starting value, and then t. So this is another notation. So you can use both. So what's the graph of this one? So you can see it's very similar, but this is the shifted version. So let's assume. This is the value of a. So that's the value of a. So what's going to happen? Until a, it is 0. So until a, the function is 0, so it stays 0. So no signal, 0. And then what happens right after a is going to jump to 1 and it stays at 1. So that's 1. So that is the general Heaviside function. Um, and we can use this fact to represent a piecewise function using this function. So yeah, so what are these two functions? So this is the ut function which changes at 0. This is the ut minus a function. A can be positive or negative. I just pick this value. So but at that point, what's going to happen? The function jump to 1 and then it stays at that value. So these are what we normally call the switching function. So let's try to use the switching functions to write several piecewise functions as a single function. So let's do that next. So, so as an example, so let's say use the Heaviside function. Use the Heaviside function. Heaviside function. Use the Heaviside function to rewrite. To rewrite ft as a single function. As a single function. Because we need to do that to use the Laplace transform. So as the first example, let's start with something like this. So that's the first one. Say I'm going to give you the ft like this. So the ft is sine t if t is greater than or equal to pi, and it is 0 if t less than pi. So always if you look at the graph, it can help you. So let's look at the graph of this function. So it looks like this. So you can see until pi, the function is 0. So it's a sine, but it's just 0 until it is pi. So go like that until pi. But right after pi, what happened? It's going to follow the sine graph. So it's going to go like that after pi. So that's pi. So and until that value it is 0. So you can like highlight it 0, and then at pi, because at pi it's 0, so it's gonna like kind of continue in this case. So it's like a continuous, nice continuous graph. So that's 0, and then this is 2 pi. It's gonna continue. So this is a switch. So the switch is on right after pi. So now what we're gonna do is we can use the Heaviside function for that. So what we want to do, you want to switch on. You want to switch on at pi. So if you want to switch on at pi, what we can do is you can use ut minus pi. Because once you use ut minus pi function, what's going to happen right after pi? It's going to jump to 1. So and then you multiply by the function that you have. So what we're going to do, so the trick is you can write this one as ut minus pi. So that's a switch, and then you multiply by whatever the function you want. So you can see this is just one single function. It's a product of two functions. But what's going to happen at pi, this part simply going to be 1. This part simply going to be 1 after pi, so it is 1 times sine t becomes sine t. Before it is 0. So that's the trick. So let's look at more examples. So let's look at another one. Let's say ft. I just ft for everything. Let's say which is 4. If like on the interval from 2 to 3. So let's say in this interval, so what I'm going to do, I'm going to remove this equal sign just to exactly match with the definition, but it doesn't really matter. It doesn't matter what happened at one point because these are integrals, and then there's no effect from a single point. And then what happened at 0 otherwise? So 0 otherwise. So that means if you look at the graph, so this is the shape of the graph. So it's like a pulse here. So we have 0 and then we have 1, 2, 3, 4. So is it 1, 2, 3 and 4? That's a t. And then the function is what's going to happen? It jumped to 4 at 2. So jump to 4 at 2 and open at 3. So that's 4. So that's the function. So it's quite interesting. So what happened? So you can see jump to so switch off everywhere else, but it exactly jump to 4 at 2. And then again it close at 3. So that means you need to kind of think about what we can do. So that means you need to switch on at 2. So to switch on at 2, what we're gonna do, we're gonna use ut minus 2 function. So what's gonna happen when you have ut minus 2 function? It's gonna switch on at 2. That's the on part. And then, but you want to make sure that it's going to switch off at 3. So how to do that? You're going to subtract a very similar function which ons at 3. So you know that at 3 this is going to be 1. So but what will happen then after 3 both are 1, but you subtract, so it's going to be 0. It's going to switch on. So that means, so this is the on function. So this is the on function and that's the off function. So we can always, if you have an interval like that, you can write a on function and off function. So it's gonna switch on only in that period, whatever the numbers that you have, in this case 2 and 3, only on that period, and outside is 0. So these are what we call switches. So this is switch, the switch. So let's do that now. So we can see it's very simple again. So what we want to do is we simply multiply by this function, whatever the function that we have. So it is 4 times, you're going to multiply by the switch. So it is u t minus 2 minus u t minus 3. So that's the idea. It's very simple. Good. So let's look at another example. So you can see just one single function that's work as a nice switch. So see, let's look at 3 functions. So let's see, we have ft, which is t if t is in the interval 0, 1, and then which is 2 minus t if t is in the interval 1 to 2, and then 0 otherwise. 0 otherwise. Good. So we can do the same trick here, but now we need 2 switches. So we need a 1 switch for some other 2 switches here. So we need a 1 switch that's gonna switch on from 0 to 1, and we need another switch that's only switch on from 1 to 2. So those are the 2 switches we need. So one switch is from 0 to 1, and the other switch is from 1 to 2. So we can use a similar argument here. So for the first one, we can write u t, which is switch on at 0, minus u t minus 1. For the second one, which is u t minus 1, which is on at 1 and then off at 2. So this t minus 2 is whatever the number that you have. So you're going to put those 2 numbers. So those are the switches that we need. Now what we're going to do, we're going to simply multiply by that. So when you multiply, so you're going to get the first function is t multiplied by the switch, which is ut minus ut minus 1, and then plus 2 minus t times, that's the second function, multiplied by the switch, which is ut minus 1 minus ut minus 2. Now what we can do is, so we write the two functions, we can distribute, we just multiply, distribute them, and then collect the terms. For example, you can have ut terms separately, ut minus 1 terms separately, so we can separate them. We can have ut terms and ut minus 2 terms, and also we can have ut minus 1 terms, because you can combine those two. So once you collect those terms, so you simply end up with this function. So you finally you have t times ut, that's the only ut function, and then we have plus, you can combine the ut minus 1 function. Once you combine ut minus 1 function, you can see from the top you have minus t, in the bottom you have 2 minus t, there are 2t minus 2, so that means you're going to have plus, so this is a plus sign, plus you have 2 times 2 minus 2t times ut minus 1 function, and then plus finally you have just one function uh, for 2 minus t, but with the negative sign here, so there's a negative sign here. It become, you can switch it, so you can write this one as t minus 2 times ut minus 2. So that's the final answer. That's just one function, but that's a switch for this piecewise function. So it's not that difficult, but you need to kind of make an argument. So write the switches and then multiply by that. So that's how you do like several piecewise functions using the Heaviside function. Now what we can do is we can use these ideas to solve a differential equation. So when you get a piecewise function, the first thing that you do is you can write as a single function using the Heaviside function. Okay, after we do that, then you can think of the transform. So that means the next step would be the transform. So let's look at the transform of the Heaviside function. So let's recall some of the things that we already know. So the Laplace transform, Laplace transform. One thing that we already know is the Laplace transform, the Heaviside function that we talked about earlier. So which is it's the same thing as, I'm just going to recall, it's the same function, the hat function, which is e to the minus as over s. So that's the function, and if you remember the graph of this one, so what's going to happen is going to switch on at a. So it's on at a, so it's going to go like that, close and open and close. So that's the function that we have. So the Laplace transform, that one is e to the minus a so s. So think of a way to remember that. So you can see there's a special word there, and then you can use that to remember. Good. Now what we're going to do is let's talk about what's going to happen in a general case. So we have a theorem. This is what we normally call the second shifting theorem. So let's talk about that. This is a second shifting property. Shifting. Second shifting property. Second shifting property. Second shifting property. So let's say we have a f, which is a piecewise function. So let f be a piecewise function. Be a piecewise function. A piecewise function. Piecewise continuous. Piecewise continuous function. Piecewise function. Then what we have is the Laplace transform of u t minus a times f t minus a. You can see they have the exact same format. this is simply equal to e minus as times the Laplace transform of the original function ft. So in other words, this is e minus as fs. So what we're going to do, you think of the Laplace transform of the original function without the minus a part, and then you simply multiply by e to the minus as. So that's the formula. So let's put that in a box. Good. But this you need to remember this formula, and then yeah. Oh, you can write the same thing using the Heaviside function, because you can replace ut minus a with the Heaviside function. Okay, because some people write it like that. So let's see how to prove this one. So I'm going to talk about the proof. This is like very simple proof. So what we can do, you can use the definition. So the Laplace transform of u t minus a over f t minus a. So by the definition, this is simply equals to 0 to infinity the functions t minus a, f t minus a, and then what we normally do, e to the minus st always times dt. So that's what we always do. We can multiply by st, e to the minus st, and integrate from 0 to infinity. Okay, now we think of the definition of ut minus a. We know that ut minus a is 0 if t is less than a. So what we're going to do, we're going to split this integral in two parts. The first integral go from 0 to a can be even negative, a. But in that case, we know that the ut minus a is 0, so that means you simply get 0, integrate 0 from 0 to a. And then plus the other part is going from a to infinity. So that's the second part. In that case, what will happen if you have a to infinity? That means if t is bigger than a, ut minus 1 equals to 1. So you can see that this part is simply equals to 1 in that case. So that means it is simply 1 times the function f t minus a e to the minus st dt. Okay. So that means we pretty much done. Now what we're going to do a simple transformation, simple like u sub. So what we're going to do, we're going to pick this part, t minus a part, and we're going to call this is simply, u. So we're going to use a substitution. So we're going to say this is u, this part. So this is the calculation part now. So what we're going to do, we're going to pick u equal t minus a, the substitution, and then we take the derivative. So du equal simply dt, because a is a constant. So after we do that, and then you can also see that t is equal to u plus a, t equals to u plus a. So we using this, we can rewrite the different integral now. It is going from, okay, what are the limits now? So when you plug in a, you can see that when you plug in a for t, this become u a minus a 0. So that means the new limit gonna be 0 to infinity. Infinity does not change. And then f, we know that t minus a equals to u e minus, what is t? T is equal to u plus a times s, and dt equals to du. Now what you can do is, you can see e to the minus as you can pull out. So we're going to pull out e to the minus as from the integral, because that does not depend on u, and write the rest now. So it becomes 0 to infinity fu e to the minus us, or su if you want. If you want to write it, you can switch it. So if you switch it, this becomes su du. And you can see that the second part is simply the Laplace transform using a new variable. So it doesn't matter what the variable is when you do the integrals. So that means this is simply says that this is simply e to the minus as times fs. Okay, so that's proof. So it's a very simple proof. um, it's only use the definition of the um, Heaviside function and the u sub. So we simply use a u sub and the definition of the Heaviside function. What we did was we split the integral from 0 to a, from plus a to infinity, and then 0 to a part is 0 because in that plus the Heaviside function is 0, so that part is gone. In the other one the function is simply 1, so multiplying by 1 doesn't do anything. So that means you only end up with f to the ft minus a e minus e to the minus st. Now what we can do, we're going to simply substitute for t minus a. We're going to call t minus a is u. So once you do that, you can see you get an integral. You can pull out e to the minus a's because that's a constant now. It does not depend on the variable. So that means you end up with the function u, but that's just a dummy variable. These are what we normally call dummy variables. So integral does not integral is independent of the dummy variable. So because of that, the second part is simply the Laplace transform of the function. So we can write it like that. So that's the proof. So it's a very simple proof, but have a lot of applications. So now let's look at the first application. So as the first application, we're going to solve this problem. Okay, so the applications. We're going to solve two problems, just two. So the first one is solve the initial value problem. Solve the initial value problem. X double prime t. I just put t just to exaggerate, but you can ignore that. Plus xt equal ft, and we assume that just for simplicity, we assume that the conditions are 0. So x0 equal 0, x prime also equal 0. Both are 0. Where the ft function, the input function is, let's say, which is 1 if t is in between 1 and 5, 0 otherwise. So let's see. Now when you get a problem like that and you know this is a piecewise function, so the first thing that you have to do is you have to use the Heaviside functions to write this as a single function. So do that. Let's again look at the graph of this function. That's always a good idea to do every time. So we have 1 and 5. Between those two values, what's going to happen? It's going to jump to 1 at 1, and it's going to switch off at 0 at 5. Okay, so that's the function. That's the ft function. So we can use two switches for that. So that means so the answer. So we can write ft like this. So ft is going to switch on at 1. So that means u t minus 1, minus is going to switch off at 5. So it's t minus 5. Okay, so on at 1, off at 5. So that's the one you want to remember. That's the on and that's the off. So if you have some other function, instead of 1, let's say you have t or something, you're just going to multiply by that. That's how we do. Okay, now what we can do, after we do that, then you can write your differential equation like this. So so then you can write the differential equation can be written as x double prime plus x equal u t minus 1 minus u t minus 5. Now what we can do, we can take the Laplace transform. Okay, so taking Laplace transform, since the initial conditions are 0, things gonna be easy. This is simply gonna be s squared xs plus xs. The reason is initial conditions are 0, so you don't see anything else. And then this one, we know this is the u function, and then we know the Laplace transform of that. So it is simply in this case So we talked about that earlier, like, what's the Laplace transform of such a function looks like. So I'm going to recall that simply here. So what was that? So we have Laplace transform of u to the t minus a, which is equals to e to the minus as. So we have minus minus, remember this time, and then divided by s. So that's the Laplace transform that. So we can use that fact here. In this case, one a equal 1, the other one a equal, in one a equal 1, the other one a equal 5. Only the when you have the eat function, remember the eat function, that gonna switch the sign. So let's write that just to remember. So when we have Laplace transform of e to the minus at, when here e to the minus at, it is simply what happened, f s plus a. So that has the opposite sign. So remember these two at the same time. So the eat function has a plus sign, the opposite sign, but here we have the exact same sign. Good. So, and then using this fact, then we can write this one as the first one you can write as e to the minus s, because a equal 1 over s. The minus sign coming from the function. So you see that there's a minus sign here. That's that minus sign. And then we have e to the minus 5s over s. That's the 5 you have here. So that's the 5. Okay. So we use that transformation formula that we discussed earlier. Okay, so everything is good. So that's the Laplace transformation. Now what we're going to do is you to solve for Sx. That's it. Okay, so we're going to solve for Sx. So that's what you want to do. Okay, we're almost done. So let's do that part and learn how to do it. Same thing as we did before. There's nothing new here. So this side is going to be s squared plus 1 times sx. On the other side, what we have is e to the minus s over s, e to the minus 5s over s. We normally do not combine these two. We try to leave the terms with different exponential functions separately, because that's exactly what's going to happen later. So now after we dividing, we can divide both sides by that term. Once you do that, your sx going to be e to the minus s over s times s squared plus 1 minus e to the minus 5s over s times s squared plus 1. Okay, so we have already solved the solution in the Laplace domain. Okay, this is the solution. This is the solution in S domain. S domain. So now what we want to do is we want to convert this into the time domain. Okay, so do that. What we normally do is we can look at the partial fractions when you have fractions like that. So I'm going to skip the partial fraction part right now because you are expert in that right now. You know how to do it. So let's say I'm going to say note that. Okay, so note that because I want to exaggerate on the argument here. So otherwise we will focus on something else. Okay, so note that 1 over s times s squared plus 1, the partial fraction is simply, you can see, you can find it, you will end up with 1 over s minus s over s squared plus 1. So that's what happened. Okay, I mean you can even see it. So that's a partial fraction. Okay, that's a partial fraction. So now what we can do, first thing what we do is we try to find the Laplace transform of that, inverse Laplace transform of that first before we invert the actual function. We can have the inverse of this first. So it is 1 over. So after we break into partial fractions, it's very simple. So the first function 1 over, that means it is 1. So what we can do is we know that by the linearity we can break this into 2. So I'm going to write it. If you forget what's going on, so we can write the first one minus the second one because they are linear, and then what we can do is from the first one, 1 over s means 1. The second one which has a s in there, so that means the other one, that means the cosine. So the cosine omega equal 1 in this case is omega. So it's 1 minus cosine t because omega equal 1. So 1 minus cosine t. So that's a function. Now what we're going to do is, now we're going to take care of this part. Now we are going to take care of that part because we know that in the second shifting property, when you multiply a function with the Heaviside function and take the Laplace transform, what it does is it just introduce the exponential term. So that means now we can go backward because we know what is the functions are. We know what these function represent in the inverse because it is simply 1 minus cosine t. So that means since we know the function, what you only need to do is you need to simply multiply by ut minus a, and then you change the variable to t minus a. So you have to do that at the same time. So simply change t to t minus a in this case. Okay, but there are two functions, we're going to consider those two separately. So using the second shifting property, using the second shifting property, we have L inverse e to the minus s over s squared plus 1. This one we can write as, now we know. So it is, what you want to do is you have to do two things at the same time. You want to replace t by t minus a. That's how we do. So what we do is we can replace t by t minus a. So you know, if identify what is a, so that a is coming from the exponential part. In this case, in the first one, a is equals to 1. You can see the first one a is equal to 1. In the second one, a is equals to 5. So let's do that separately. So the first one, you replace each t by t minus 1. So that means it's going to be 1 minus cosine, you replace t by t minus 1. And then you also multiply the whole function by u t minus 1. That's the second shifting property says. Whatever the function, replace it by t minus a. And then also multiply by this extra function t minus a. Okay, a equal 1 in this case. That's the first one. Now do the same thing. So let's look at the second one. If you look at the second one, so what happened? So it is e to the minus 5s now over the same function, fortunately. So that means you still go to the same function, but now you replace by t minus 5 because a is equal to 5, and then also multiply by u t minus 5. So that's where that's coming from. So you can see that it's not a difficult argument, and then that's it. So that means those are the inverses of the two. So that means if you look at the inverse Laplace transform, now you have the answers for that. So that means by taking inverse Laplace transform, so we can write the solution now. So we have now by taking inverse Laplace transform, so we have xt, which is simply the L inverse of xs. So this is simply going to be, we know that L xs is, you break into 2. So let's write the 2. I'm just writing all of them just to make it clear, but you can skip some of them. So it is e minus s over s squared plus 1, and then there's a minus sign there, and then L inverse of e to the minus 5s over s squared plus 1. But we already found those two, so what you want to do is you want to plug in them here now. So the first one is simply 1 minus cosine t minus 1 times u t minus 1 minus the second one, which is 1 minus cosine t minus 5 times ut minus phi. Perfect. What we normally do is we try to kind of write them as one function if possible. So what's going to happen? We're going to consider separate different cases. So what's going to happen, because you have two numbers here. One number is 1, the other one is 5. So that means you can split them. So what's going to happen before 1, what going to happen in between, and what can happen after that. So that means you can write this one as a single piecewise function. So what's going to happen? So if t less than 1, everything is 0. So but at between 1 and 5, only the first function is on. So but between 1 and 5, you only have the first function, t minus 1 function. This is if t is in between 1 and 5. And then after 5, both are switched on. That means you can put, for the ut minus 1 and ut minus 5, you can put 1. That means you can simplify this. That means this 1 get cancelled because there's a negative sign. So 1 get cancelled, and then also the negative, there are two negative signs. So that means the cosine t minus 5 going to be positive minus cosine t minus 1. So this is if t greater than or equal 5. Okay, so that's the final answer for this one. This is just a simple algebra. So what we did, we considered two different cases. So what's going to happen if t less than 1? If t less than 1, everything is 0, so you don't get anything, it's just 0. And then in between 1 and 5, you have only the function 1 minus cosine t minus 1. And then if t greater than 1, you're going to see that both switches are on. So that means you can simply simplify the two functions. So then 1 get cancelled, you only end up with the other function. Okay, and then you can see that outside this 0. So actually you can also add that part. So I'm going to write it. I'm going to write that also. I can say 0 otherwise. What is otherwise? Because we need to know what's going to happen before 1, because it's 0. So that's exactly the situation for this function. Okay, so let's look at the graph of this, how it's going to be, because you can see that it has to be 0 and exactly at 1 it's gonna visible. Okay, so let's look at the graph of this function. So so you can see the graph looks like that. So you can see at exactly 1, it's gonna start. So that's 1. So you can see at 1, it's switch on. It's gonna switch on, and then it's gonna be 1 minus cosine t minus 1 until 5, and then at 5, what's gonna happen? It's gonna come to the other function. Okay, so it's gonna say it's gonna stay with 1 minus t minus 1 from 0 to 5, and then at 5, it's gonna go with the other function. You can see that they have two different heights, so that clearly says it's gonna switch to a different function after that. Okay, so that's the solution to the first problem. So let's look at just one more example just to see how things going on. But the theory is exactly the same, so nothing much. Just one other example just to see what's out there. Okay, so the next example. So solve the IVP. Let's say x prime minus x equal ft along with x0 equals 0, where the ft function is t minus 1 if t less than 2, and then 4 if t greater than or equal to 2. So the best thing would be like, let's look at the graph, how it looks like. Um, so what's the shape of the graph? So I'm going to graph it here. Um, so until 2, it is t minus 1. So until 2, it is t minus 1. So that means it's going to go like that. So that's the number 1, negative 1 there. Okay, that's negative 1. But this happened until it is 2. And then right after 2, what happened is going to jump to 4. It's going to jump to 4 and going to stay there. So that's the situation. That's the input function. So the goal is, what is the output function? That's what we're trying to find. We try to find the output function. Same argument. What we're going to do, we're going to have, we need switches. So this problem may be slightly different. How to do the first part? So you can see that the first part has to be switched off at 2. So how to do that? So what you want to do, the switch for the first part has to be, because it has to switch off at 2. So what we can do, we can use a nice trick. We can do 1 minus ut minus 2. We write it like that. Because if you have a switch like that, 1 minus ut minus 2, you can see that at after 2, that is 1. So 1 minus 1 is 0. So that means that part is gone. So now what we can do, we can multiply the function with this switch. So that's a switch. And then for the second part, what we need to do is, because this part is gone after 2, we just multiply the 4 with the switch. For that part, is switch is simply ut minus 2. So let's do that now. So we're gonna say the answer. First, you can see we can write the ft using the switches. So the first switch is 1 minus ut minus 2. So that switch is only on from 0 to 2. You're going to multiply the function t minus 1 in that period. So that's the first part. The second part, you have switch on at 2 and multiply by 4. So that part is simply plus 4 times the switch t minus 2 switch. So what's going to happen after 2? After 2, the first function is 0, and then you only get the 4 because the switch is 1. So now what we can do is we can like distribute, we can multiply through. So you can multiply through and combine. So once you do that, and you can see there's a 1 negative t, and then also you have a negative 1. This become positive 1. So with the 4, it's become 5. So that means finally you're gonna get you're going to multiply by 1, so you're going to get t minus 1. That's the first function. Just multiply by 1. This multiply by 1. And then the u function. In the u function, what I'm going to do, we're going to distribute. Once you distribute, you're going to get a minus t, and 1 plus 4, so it's a 5 minus t u t minus 2. So you can write it like that. Because it's simple, it's easy. Only the second part has a Heaviside function. Good. Okay, so everything is done. So now what we need to do is just take the Laplace transform of the differential equation and invert. Okay, so taking Laplace transform of the differential equation. So we have sx minus sx because initial conditions are 0. And then I need to take the Laplace transform of this function, it is t minus 1 plus 5 minus t ut minus 2. So be careful with 5 because 5 sometimes looks like s. This is 5. Now we just take the Laplace transform. T means 1 over s squared Negative 1 means 1 over s. Those parts are easy. And then we can use the shifting theorem. But the thing is that before we use the shifting theorem, we have to bring it to the right format, because we know that in the shifting theorem, it has a special format because it has to be u t minus a f t minus a. So they should have the exact same format, t minus a t minus a. Then your answer is e to the minus as times fs. So that means we have to rewrite the form like that. So what we're gonna rewrite it in that form. That means you need to isolate the t minus 2 term. To do that, what I'm gonna do, I'm gonna pull the negative sign out. Then you're gonna get the t minus something. That's the first thing I do. I'm gonna pull the negative sign out. So then inside, we're gonna have t minus 5. We write it like that. And then ut minus 2, ut minus 2. So the goal is to rewrite this function using t minus 2 term, because this simply equals to t minus 2 minus 3. We can write it like that. Okay, negative 5 means negative 2, negative 3. So that's the trick. So we can write that part like that. Then we can use the shifting theorem for that. So that means what the shifting theorem says, if you have a function like that t minus 2, like t minus a, just ignore the t minus a part, just multiply by e to the minus as and then fs. That's it. So that means you can simply ignore t minus 2. T minus 2 part you simply consider as t. So that means your actual function gonna be t minus 3. So the function looks like, so I'm gonna write that here. So that means in this case your function act like t minus 3. So that means you ignore this part. Just replace t minus 2 with t, because you have to bring it to the same format. So that means your function looks like t minus 3. Okay, so because of that, then we can write the Laplace transform of that. So by the shifting theorem, so I'm going to say by shifting theorem, by second shifting theorem, by second shifting theorem, by second shifting theorem. So we can write the inverse like that. So we have s minus 1 sx on this side, no changes to that side yet. So what we have is 1 over s. This is just algebra, so we just play with algebra here. Minus by the second shifting theorem, you have e to the minus a is 2, so 2s, and the Laplace transform of the function is in this case t minus 3. So that's the function. So that we can do now. So it is 1 over s squared minus 1 over s, and then we have, so we can take the Laplace transform of the inside function, which is 1 over s squared minus 3 over s times e to the minus 2s, and then we can do the common denominator. If you take the common denominator, the first two, if you take the common denominator, that's s squared, this is also s squared, so we can simplify them separately. So in the first one, if you take the common denominator s squared, you can see the second one miss an s term. So that means so what we can do is we can write this one as 1 minus s. Okay, so we can write this one as 1 minus s, because the second one means s term. So that means this is going to be 1 minus s times s over s squared. That's what you get from the first one. And from the second one, and the same thing, the second term misses, so that means it's going to be negative 3s, but with the negative sign in front. So there's a negative sign in front. We can switch the two. So that means we can write this one as 3s minus 1 over s squared and e to the negative 2s. So that's what you get. Now what we can do is we can divide both sides by that term. So that means your Sx simply going to be, so I can pull the negative sign s minus 1 from that for a reason, and this s squared you divide by s minus 1, and then plus, you can see here also 3s minus 1 over s squared s minus 1 e to the minus 2s, and you can see this term get cancelled. Sometimes that happen, not always. That means you simply end up getting negative 1 over s squared plus 3s minus 1 over s squared s minus 1 e to the minus 2s. So that means this is the solution in the so this is the solution of this domain. So the solution in S domain. So what you want to do is you want to transform this into the time domain. For that you're going to use the second shifting theorem because of the second term, because you have an e term. When you see e to the term in the Laplace transformation, you have to use the second shifting theorem. But before we do that, we only look at the partial fraction decomposition of that. Okay. So so using partial fractions, we can write. I'm gonna skip this part because you are good in this now. Okay, because let's focus on the argument. So if you use the partial fraction, you simply end up getting 1 over s squared minus 2 over s. But if you want to do a real problem, you need to show all the work and how to get that. But when you try to use these Laplace transform in some other courses, then you are free to do anything you like. But here we are learning, so you want to make sure that you show the steps. But this is exactly what's going to happen if you try to find the Laplace transforms. So that means then we can find inverse. So we can say thus the inverse Laplace transform of this. So we're going to find the inverse. So it is 3s minus 1 over s squared s minus 1. So let's go one by one. The first term says it is t. The second term says it is 2. So the next term says 2. We have a. This is the eat function. So it is a equal 1. That means it is t. So remember, it's always the opposite sign. Okay, so that's the function. Now we can use the second shifting theorem. From the second shifting theorem, what we want to do is we know that the a is equals to 2. So that means we're going to replace each t. We can replace each t by t minus 2, and then multiply by e to the then multiply by u to the t minus 2 also. So that's it. Okay, so now we can use the second shifting theorem and we write the final solution for that. Okay, so that's the end of this. So let's do that part. Then we can see so then we have the L inverse. It's not difficult, but there are some writing here. 3s minus 1 over s squared s minus 1 e to the 2t. So 2s. Thus we do at the end. This is from the second shifting theorem. So so what happen is you can replace each t by t minus 2. So that means the first t gonna be t minus 2, and then minus 2 we already had that, plus 2e, you can replace t by t minus 2, and then you also need to multiply by u t minus 2. So what we can do is we can simplify. See, so we can simplify that part. So once you simplify, you're gonna be t minus 4 plus 2e t minus 2 times u to the t minus 2. Okay, good. Now what we can do is we can write the final solution, because we only consider the first part. Remember, there was a 1 over squared part we already have there. So that means we can write the final solution. So therefore, you can say therefore xt, which is the inverse of xs. So we have two functions. So what are the two functions? One is the L inverse of negative 1 over s squared. So that's what we had before, and plus this part, plus the L inverse of 3s minus 1. I'm writing all of them. Some steps are not really necessary. So for example, this step you don't, it's not really necessary. Okay, so now we can write the final answer. So negative 1 over s squared means negative t, and then the other one we already know, it is t minus 4. No, let's not write like that. So t minus 4 plus 2 times e to the t minus 2 times u t minus 2. So that's the final answer. And then if you want, you can rewrite them in a different way. So for example, you can see that if t is less than 2, the second function is 0, so you only get minus t. So this is what happened for negative 2. So if t less than 2, if t greater than 2, this u function simply becomes 1. So that means you can simplify these two. So in that case, what's going to happen, uh, the negative t, positive t get cancelled. So you simply end up with 2e t minus 2 minus 4 if this is t greater than or equal to 2. So that's the final answer. So this is the end of the Heaviside function method. Thank you.